Again, welcome to today is November 12th. As I was saying earlier, we have another week before Thanksgiving week. So I think I need to adjust some of the assignments so that you guys are not going to be submitting things during that week. And that should be the only thing that I can think of. And hopefully we put some few assignments also before the final, which is going to happen shortly after the Thanksgiving break. Okay, so today we're covering, let me go into the content first. Okay, where is that card? This one. So we're covering today basically chapters 27 and 28, and they have to do with color. Color, there is a theory behind it that basically we need to somehow cover it a little bit, and how colors mix to make up different colors. That's at least from our perception. And the fact that the color itself is actually related to the frequency and the wavelength, to be more specific. And that is how our eyes perceive light. We have a range a little over 300 nanometers. Nanometer, by the way, is 10 to the -9 meters. So it's a very, very short distance, wavelength, all the way to some, 700 nanometers is when the longest wavelength, the red light. So from the violet, which is super short, I think around 380 nanometers, all the way to about 700 nanometers for the red light. That is our the perception of color, at least that we get it, that we personally, I mean, we humans basically, the human eye can perceive, and that is basically what we call light. As we said before in the previous chapter, actually, light turns out to be just a small, tiny region in the entire electromagnetic spectrum. So the EM spectrum includes light, and although anything above the red, I mean, above the violet, which is in terms of frequency, of course, which is the ultraviolet and beyond the X-rays and the gamma rays and so on and so forth. And anything basically below, in terms of frequency, again, the red light, which is the infrared, of course, the microwaves, the radio waves, and all of these waves basically of very long wavelengths. So our perception, at least the eye, is into that. And again, we have quite a few basically things to talk about in terms of how light combines. One word of caution, because this is really something that is personal, and that is the fact that how we perceive light is really on a personal level. Some people, their perception of the red, or at least not some, everybody's perception, for example, of what it looks to me like it's a red color, may very well be completely different or slightly different than what you perceive as my tone or hue of the red than yours. So this is basically for on a personal level. As a matter of fact, there are people who don't even see the red, you see it, they see it gray. Those are the so-called colorblind, because again, they have this, there is a variation in this thing. So that's basically in terms of the color. But there is interesting phenomenon there, and how you combine colors, you add them, or how you subtract them, and you get with different colors and so on and so forth. That leads, of course, to technology, especially when you're a printing business and you're doing photography and things like that. That is a very important idea to work with. Then the second part, which is the chapter 28, deals really with the laws of reflection and refraction. And I know for some of you who are sitting in physics, basically 11, we have explored this idea a lot. Namely, we already have a lab on it, and how rays, when they hit a medium, when they separate into media, then in this case, they have two things that they can do. Either they reflect or they refract, okay? Or do both, actually, partial reflection and partial refraction. The idea of reflection itself is the basis for something which is very deep in technology, namely in optics, geometrical optics. A lot of the devices like we use, for example, like this glasses and lenses, cameras, telescopes, microscopes, they use extensively this science a lot. And they have to do with both the laws of reflection and the laws of refraction. Every time we mention mirror, whether being it's a flat mirror, concave mirror, or convex mirror, they are all using the law of reflection. When we talk about lenses, whether convex lenses or concave lenses, or partially concave convex on one side, or basically a flat and convex on the other side, or flat and concave on the other side. So there are so many ways that you can build a lens, basically. And those lenses, they use refraction. So that's really at least the light in between them is refracted. So it goes through from one medium, refracted inside the lens, and then comes out. This is exactly how we see objects, because we have lenses in our eyes, actually. So we have light that comes in, and it goes through the pupil, first of all, which is the little opening in the black side of the dark side of the eye, depending on the color of the eye. So that opening, and then goes through a lens, and the lens basically focuses it to a retina. The retina at that point is made up with fibers, basically, with tiny, basically hair-like fibers, and they come in two different shapes. There's the so-called cones, and the other ones are, forget the names for them. Anyway, some of them, they give you the perception of basically the shades of different colors. Black. Somebody knows what they are? Yeah, rods and cones. Thank you very much. Okay, so they give you the perception of basically the different kinds of shades of color, basically shades of black, basically, and shade and all of that. And the other one gives you actually the perception of color. Now, because light is an electromagnetic wave, we talked about the fact that it has the electric field and a magnetic field coming together. The magnetic field is super, super, super weak compared to the electric field. The magnetic field is, the amplitude of the magnetic field is usually around 1/300 millionth that of the magnetic field, the electric field. So the electric effect dominates in this case. So the electrons in those rods and those cones, basically, they respond to the electric field. You have a charge now. That is how you have a charge sitting in there. Light hits it. Depending on the intensity of the electric field in that light, the electrons either move far or move just a tiny up and down. Okay, that generates an electric signal, whether it's a strong electric signal for very intense light or a very weak electric signal. That electric signal is carried out by the nerve, the nerve, basically, and goes all the way to the brain, which gives you the perception of different colors. Okay, so that's basically in a nutshell how the theory of light is, and we talked about that and perceptions and all of these things. Now, again, we have the main piece in here that I'm talking about is the fact that we have the lens. Okay, so this is the physics. Physics really stops the minute the electrons start to move. After that, it's outside of physics. Okay, so that's, you're not going to ask me about more details on that. I don't know how things work in there. Okay. Anyway, we're going to talk about the principle of the least time. The principle of the least something is one of the foundations of physics. There is something called the least action. That is actually a different way of formulating classical mechanics. There is the least time, which is due to Mr. Fermat. This principle basically tells you the following. Light, in going from point A to point B, takes the shortest time. That is basically the principle behind it. Using this principle, okay, it's like a law. Using this principle, we can explain the law of reflection. We can explain the law of refraction. We can even explain for how light, for example, goes from one side of the lens to the other side of the lens and reach and focuses on a specific point. So we can even understand how we can get a sharp image, for example, using a camera. So this is the least principle, and it's a very powerful principle. It's just based on this simple statement. You have point A, you have point B. Light takes the least amount of time going from point A to point B. End of the story. Okay. Isn't this a simple principle? What do you guys think? The least time principle. Okay, so that's topic number 1. Okay, so state the least time principle. Light when it goes from point 1 to point 2 or point A to point B takes the least time. I'm saying the least time, not the smallest distance. Okay, not the shortest distance. Okay, it has to do with time. Okay, so the time in here needs to be as small as possible. Okay, so this is the least time principle. Sometimes also is called Fermat Principle. Okay, so let's write it like this. Okay, named after Fermat, who discovered it and later on used it. At some point, we probably are going to mention Huygens principle, which is slightly different, and also can interpret this one and also come up with the explain to us the phenomenon of interference, namely the laws of diffraction, namely the laws of single slit, double slit, and all of the other things that are related to how light basically interfere with one another. If we have that understanding of Huygens principle, which is slightly different version of this one, and also explains this one, explains the phenomenon related to laws of reflection and refraction and how light bounces off of the medium and goes to the other one. Okay, so you guys got the topic number 1? State the principle of the least time. And the principle of the least time basically is that time takes in going from point A to point B, light takes the least amount of time. Okay. So, and we're going to get into it. So we're going to talk about the law of reflection and the law of refraction. Per Mr. Feynman, one of the criticism that was basically that was given to the Greeks is the fact that they didn't do a lot of experiments. They did a lot of thought experiments and principle of this. They did well in mathematics because it's all based on thinking and philosophy, of course, and governance and all of other things. But they did not do in science, especially in physics, any kind of experiments. They did most of the time just basically thought experiments about the fire and the elements and how the earth is made up of and the laws of motion, but they didn't do much experiment. The only documented experiment that was, according to Mr. Feynman, is the law of refraction. So basically what they did was, on the surface of water, they had sent beams of light, and they noticed how beams of light is broken. And they documented it. They vary, in this case, for example, the incidence, what happened to the refracted beams. So that was the only thing that was ever documented by the Greeks, according to him, that they did actually in actual experiments to really come up with some sort of a law there. These two laws are sometimes called Snell's laws, okay, named after Mr. Snell, who made them, basically wrote extensively on them. Of course, they were not discovered by him. They were known before him. So let me share with you the name, how you spell this. Because again, I'm using this pen today, and it doesn't write well on PowerPoint. Okay, so his name is, oh man, it's on. Oops, I need to be here. Snell. Okay, so it's sometimes the first law is called Snell's law of reflection, and the other one is Snell's law of refraction. Then we're going to talk about dispersion, which is an interesting phenomenon. When you have a white beam of light, okay, white beam is really, we'll see from the color theory, is that it's a combination of all of the other beams, of all of the other frequencies. But because the frequencies now have different wavelength, the minute they hit a different medium, they refract at different angles. So now the light is basically split. It's not the same. So now you will see the rainbows, similar to what you see when you take, for example, a CD or a DVD and you put it on different angles, and you will see the different colors showing. And that is because at this point, light, when it refracts over the linings of the CD or the DVD, you're going to see the grooves in the DVD, you will see the different frequencies on it. Or when you have a fresh oil leak, for example, or some oil on the ground, and then you have water on top of it, underneath of it, of course, there is water and there is the oil, you will see all kinds of colors in there forming, okay, different mixture of colors in there, okay. That is because the light that is coming from the sun at that point and the outside is hitting that surface, and light is coming, of course, mixed with all of the frequencies, but when it bounces back now, it bounces with all of different angles, and you will see, especially when you turn back and forth, you will see all kinds of different colors in there. Did any one of you experience this? Whether you're talking about the DVD, you look at it with different angles, or with the oil, especially when the ground is wet. Yeah, after rain, when you have rain, but there is oil on the surface, so you need the surface, okay? You need, of course, rainbow is another phenomenon also that has to do with that. I think a few days back when we had the rain, I saw the rainbow on Saturday. That forms again because of that. So we're going to talk about that. And finally, we're going to talk about the total internal reflection. This happens when you have a medium that has a higher index of refraction basically. Like, for example, you are under the water, and and that's where the incident beam is coming from, not from the one that has a lower value of index of refraction. Now, when it goes back, at that point, you saw from the experiment, at least for those who are sitting in physics 11, you saw that the angle can vary from 0 all the way to 90 degrees, whereas the other angle is limited from 0 to a certain number depending on the index of refraction. So imagine yourself coming from there and then going from the other side, it's going to come at 90 degrees. That is the angle of total reflection. So you cannot have a refraction if you come anywhere greater than that angle from the other medium, okay? Another idea also for the principle of Fermat, in here, since we're talking about the total angle of reflection, is that if you find the shortest distance from going from point A to shortest time from going to A to B, it's the same shortest time going from B to A, okay? So principle of Fermat doesn't care which way you start, whether you start from A to B or B to A. So if you find the path being the shortest distance from A to B, that is the shortest time. I'm sorry, again, I'm telling you, warning you about that, and I'm falling into it. So the shortest time between A and B is a certain path, then the shortest time from B to A is the same path. Okay, so you have to be very careful with that too. So that's actually an idea in there too. Okay, it doesn't matter which way you shine. Basically, if you take a flashlight and you shine it from here and you see the beam is bouncing on the other side, if you go to the other side and shine it, it's going to come back to exactly where you were sitting before, okay? We're going to talk about lenses, and there is a problem with lenses because of the dispersion. Because when you use lenses, for example, in telescopes or even in cameras and things like that, you have a problem. Because light is coming, all of it the same frequency, I mean, mixture of frequencies, of course, coming to you. Once it hits the lens, then when it comes out, you want it to be all focused in a single point, especially when you're dealing with a telescope. You want it all focused in a single point so that you collect all the light there and analyze it. But what happening here is some of the lights, they deflect more than others. The red light deflects most, and the blue light or the violet light will deflect the least. And now you have separation of frequencies. In other words, the beam that comes out doesn't go all to the same points. It's going up and down in different places, and this presents a problem for telescopes that use lenses, okay, not mirrors. There are two kinds of telescopes, basically. There is the so-called Newtonian telescopes that use the law of reflection. They use mirrors, and those are good because they don't have lenses. But there are telescopes that don't use that. They use actually the law of refraction. They are refractive telescopes, and they're usually they are longer. And those have this problem because as the light comes in, the image is kind of separated, and you will see the object with different colors separated, and you see a person in front of you with different things. So this is a defect, actually, and you'll have to make corrective lenses actually to bring back the beams back to where they were. So if the lens that you were using was a was a focusing length, basically. Converging lens, it's a convex lens. You need to have a diverging lens, which is a concave lens, at the end with just the right focal point to bring the beams back into focus. So this is, in a sense, in a nutshell, the entire chapter. I think we're done. What do you guys think? 2 chapters, actually. So let's get into a little bit of details. I hope I have more than one student in the class. Seems like only Kyle is responding to me right now. Everybody else is taking it easy. I hope you guys are here too. Okay, so again, color, I was mentioning the fact that there is actually an effect with it and there is our perception to it. And it has to do also with how well you think you see color and all of that. But the main thing in here, it depends on the frequency of light. As a matter of fact, it depends frequency of the wavelength, because that's the same thing, really. Because remember, when we took the waves, the frequency times the wavelength is a fixed number. It doesn't change, okay? It's the speed of light in this case, okay? So there is this fundamental law. Please do not forget it, okay? It's a very important law that is a very, it's actually called the Dispersion Law. So I really needed to bring it back to your attention in here, because we discovered this a few weeks back. I hope that we did. I don't remember now when did do that. So the frequency, which is usually the letter F, so this is the frequency, times the wavelength. And the wavelength is actually the Greek letter lambda. So this is the wavelength. In vacuum, this is 300,000 kilometers, but I cannot use kilometers. I have to use meters per second. So this is a fixed number. So if the frequency is high, for example, the ultraviolet, its wavelength is short. That is in a nutshell what this expression is saying, okay? Because their product is a fixed number, it doesn't change. Their product is always 300 million meters per second. That's the speed of light. So it depends on the frequency, of course. So from low to high, in terms of frequency, we have the red, followed by the orange, the yellow, green, blue, indigo, and violet, okay? There is no white color at all in the mixture in here. That is because the white color is a mixture of all of these frequencies, okay? Beyond, of course, violet, there is the invisible ultraviolet, and below the red light, there is the invisible also ultraviolet, okay? I mean, infrared. What can the human eye not see? Anything infrared, we cannot see it. Okay, it doesn't matter. Ultraviolet also, we cannot see it. That is anything below the red, and anything above the violet, we cannot see. So the correct answer is A and B. Brings me to an interesting thing. I always think about this one when I get in here. Other animals do not have necessarily the same perception of color. That's something that you have to. As a matter of fact, dogs, for example, they don't see the same colors as we see them. Okay, they're, at least for our eyes, they look like completely colorblind. So that's their perception of things. And the other thing also, that when you come to this point, when you're talking about frequencies and what we cannot see, it really has to do with the fact that we're living on planet Earth, which is near the sun, and the sun peaks around these frequencies. That is the main bulk of our the frequencies emitted by the sun. As a matter of fact, the sun has this curve. It's a bell curve, and it's peaked around actually the yellow color, and that's what our eyes also are peaked in terms of our perception of colors. If we happen to be probably living in a different planet, like for example near Proxima Centauri, which is really super dark red planet, then maybe our perception will be toward the lower frequencies, not this high frequencies. Not this at least the higher frequencies, I should say, not high necessarily. So this is an interesting thing also. If you happen to meet aliens, they may be completely blind to the colors that we see and see things that we don't see in the dark, and vice versa. So they may be walking in the dark perfectly all right, and during daytime, the things looks to them completely fuzzy and they cannot see. And this makes it interesting for a sci-fi book on meeting the aliens. But it seems like all the aliens we meet, they are perfectly fine during daytime, and they tend to sleep also during nighttime, which is kind of weird. They should not do that. Okay, that's because it's the lack of our imagination. Okay. Okay, again, we're talking about how the colors mix in here. Okay. The fact that you're looking at an object and you see it with that specific color, okay, means that it's actually reflecting mainly that frequency. It's absorbing everything else and reflecting that frequency. So that's why, for example, the ball in this case looks like it's an orange ball, okay? If you shine on it the red in this case, or the red in this case, if you shine on it on the red in this case, it's reflected for the entire surface. But if you shine on it the green, for example, in this case, it's absorbing it, and that's why it looks like it has no color in this case. It's lacking color because it absorbs the green in this case, whereas the background behind it is reflecting the green. For the transparency, it's the opposite in this case. Okay, when you have the transmission is the opposite of the reflection in this case. Okay, so if you have white light coming from the other side, and then you see only the blue, that indicates that this glass in this case, that's probably shaded with blue, can transmit everything. I mean, can absorb everything except the blue in this case. Okay, so it's transmitting the blue in this case. Again, this is the bell curve more or less of the one that I was talking about in here. Anything above one side in here, that is the ultraviolet. Anything on the other side is the infrared. And our eyes also peak toward the green in here, yellowish green region, and that is exactly how the sun actually emits frequencies too. This curve is divided more or less into these three fundamental colors: red, green, and blue. These are the so-called Rgb colors. R for red, G for green, and then B for blue. Using these colors, you can obtain any colors you want. For example, you have in here the red and the green. They give you the yellow. The red and the blue, they give you the magenta color. The red and the blue and the green, they give you in this case the cyan color. And all of them mixed together, they give you what is called the white color. Okay, the perception of what looks like it's white. It's all of the colors basically being reflected in this case. So if you're looking at the screen right now and looking at the white screen, at least their surrounding, that is because all of the frequencies, or at least the three frequencies, the main ones, are coming back to you. In the industry, okay, you're talking probably, Kyle, about the different standard in this case, the Y, what is it, the yellow, cyan, and the magenta, YMC, and then the letter K added for the black one for the color in the industry. Those are the primary colors. So you could use the RGB in this case as the primary colors and mix them, or use the YMCK as the basis for your color mixtures, in which case you can obtain the red then by removing one of the others. So if you go back into the slide, then you can still obtain the red. So there is the subtractive, and there is this subtractive, and there is the additive colors. So we're talking about the additive at this point. Okay. So yeah, I mean, there is all kinds of things about this one. And again, this is technology. It's not really basic physics, to be honest with you. So, and how you mix these things and perceive the different colors and all of that. Okay. So red, green, and blue light overlap to form, in this case, the white light. We can clearly see from that. How are we doing on time? Well, we spent already half an hour on this, but we did a big introduction. So usually we do a lot of introduction and then we move faster through things. Again, all of these questions have to do with that previous one. When the color yellow is seen on your color TV, the phosphorus being activated on the this is talking not about the modern day technology, because it uses different technology completely. It's talking about the other the tubes, basically, the old tube TVs. Okay, yes. Because they had fluorescent material on the screen, and they're sitting in there waiting for the electrons to hit it, and it activates, depending on the frequency that is they come with it, then they activate the, or the intensity where they come to activate the specific colors, either red, green, or blue, and then from there they mix to give you all the different colors. Of course, now we're using digital technology, which is used different bases completely. So this question is an outdated question. What is it? Yeah, this one. And in here about the subtractive. So I'm going to skip a little bit because this is actually, again, for the printing industry, they use the magenta, the cyan, and the yellow, the Y, M, C, and then they add to it the color K, which is basically the black color, to make all of the different colors. Because if you do that, and you add to it the black color to give you the different shades, basically, of gray, then you have the perfect, in this case, setting for the pictures. As a matter of fact, there is a picture in here that is taken with different, basically, colors. This is the magenta. Then you add to it the yellow. Then you add to it the cyan. Now you have this color. Of course, it looks like it's kind of burnt color, unless you add to it the K, in this case, the black, and then at the end, the picture looks sharper and perfect. So this is in the printing industry. And this is, again, I would encourage you to go more and look into this subtractive primary colors, okay, versus the additive colors, and see how they work in this case. Okay. And why the sky is blue? Well, in this case, it has to do with the frequency that is coming from the, how basically all light, when it hits particles in the air, and it's diffused, okay? Imagine that you have particles or water droplets in the air that sit in the atmosphere. So during the daytime, when the beam is coming from the sun, the ray that scatters the least, in this case, or diffuse the least, I think we should really defer this question toward the end, is the blue color. So the sun will give us that perception that the sky is blue. But the one that diffracts the most is actually so let's answer this question, because this is an interesting question that you are at the point that you really need to explore it. So let me share with you this screen. So we are midday, okay? We're around noon. Doesn't matter, okay? We are not in the morning, the early morning or the late evening. So here is droplets in the air, and they have so many of them, of course, and you're standing in here looking at the sky. The rays from the sun, they're more or less direct coming in here. Now, the red will deflect the most. The blue will more or less go straight through. So when you look, you will see the sky devoid of the, doesn't have much red in it, okay? You will see mainly the blue color that is going to go through it, okay? So that's why, and actually there are some shades of blue depending on the day, how many clouds in there, okay? How much water, how much basically humidity in there, okay? So you have a perfect day with blue. Sometimes it's a little bit greenish. Sometimes it's different colors in there. That's really how it is. Now in the early morning though, or in the evening, okay, you're standing in here and you're looking at the sky in here, okay? And here is the sun hitting the particles of the air in here. Now, the blue will deflect the least, and they go this way, and the red will deflect the most, okay? So the red, when you look up in the sky, you see the whole sky, the whole scenery is actually going toward the red, or at least starts with the yellow, and then it moves to the orange, and then it goes to the red, and then darkens in red and goes completely white. I mean black, I'm sorry. So this is in the evening, toward the evening, or even in the morning. It starts with those different dark shades of the red, then it's red, then it goes to orange, then it's yellow, and then it starts to become bluish and bluish until midday, that's blue. So this is why, and we're going to talk about that, how light basically is refracted when it goes through water droplets especially. So it's going to come through in here, and then the red will deflect the most versus the blues deflect the least. This is the phenomenon that we're going to explore toward the end, how the dispersion of the rays are going to happen. So again, that is the answer into why the sky is blue. Which brings me to the second question. You need to explain in your own words why the sky is blue. Midday, and I already gave you the answer. And why it's orange toward the evening or in the early in the morning. Of course, on a clear night, if it's cloudy, then it's cloudy. Got it, everybody? Second question of the day today. Yes. So hopefully everybody else also is in here, okay? So we need to explain this thing. Thank you, Samantha. And Kyle too. Okay, so so we're going to skip through that, and again, it's talking about the light, the least scattered, and this has to do with the scattering I was talking about. So the least scattered is the blue one. That is why it's going to look blue during daytime, and at night, I mean the evening, the most scattered is going to go toward the red. Okay. Again, it's talking about why the water is bluish or greenish, in this case, greenish blue. So I'm going to skip through these things because we have the other part of the chapter, and I'm hoping that you guys will finish that. You will have assignments on these things, of course, please don't forget that. So we're going to talk again about the laws of reflection and refraction and lenses and mirrors and how images form. For those, again, sitting in physics 11, you have quite a few activities to do that for the lab. So again, the reflection in this case is that it hits a medium and it bounces off of the medium, okay? So that is in a nutshell what the reflection is, and it's something that you can see. Fermat Principle, I already mentioned the idea that light takes the quickest path, the least time basically, in going from one place to another place. This is called Fermat Principle, okay? The guy who stated it first was Mr. Fermat. So here is the idea. You want to go from point A to point B, and you would want to take the least time. Of course, we are excluding the fact that you can shine the light directly from A to B. That is not the question. The question is, how can you go from point A to B through a middle point? So let me share with you the other screen and explain these points. So for the reflection to happen, it has to go by a medium that is reflective, shining metal, for example. So you want to start in here and you want to end up in here. So this is your A, this is your B. And you would want to go in such a way that the least time it takes from A to B. Of course, somebody might suggest, let's go in here and hit the mirror first and then can go in here. Yes, we take the least time going straight to the mirror, but there is a long time going from because this distance is super far. If we go straight down from the source, we take less time than going through this angle. But then we're going to waste a lot of time going from this path, because this path is actually a lot longer than this path. Okay, obviously this path is longer than this one. Or another point in here that somebody might suggest, how about if we do the following? We go straight just below where point B is, take it there, and then go in here. Okay, again, we're taking a lot longer time than what we do with the law of reflection than if we just go here. But then this distance is a lot shorter than this one. It turns out the solution to this problem is somewhere in between, where these two distances are so that the angle of incidence, which is this angle, theta I, is the same angle of reflection, which is this one. So in a nutshell, the law of reflection works that way, okay? So if you're standing in front of your mirror, and I know I talked about this one, and this is a flat mirror, of course, and you're looking at the mirror, here is you, man, you're a very long neck, I'm sorry about that, okay? I don't draw well, anything, okay? And you're looking at the mirror. Let's say, for example, you want to see your feet. Okay, let's say this mirror is super tall, that it is as tall as you are. So here's your feet, okay? So the ray that comes from your feet and hit your eye follows the law of reflection. These two angles are the same. For you, it looks like the image is coming from the other side. This is what your foot looks like. Now you look at your hand follows this law of reflection coming to your eye. Again, the angle of incidence is equal to the angle of reflection. You think that the hand is coming from the other side, where this distance is the same as the other distance, but extending through the other side. If you continue this way, you're going to remake an image of yourself on the other side. I'm going to try to draw the same thing that looks identical to the object in front of it. The distances are the same. Okay. And the image is upright, actually, standing on its feet, just like you are. And the magnification is 1 in this case because it's same size, okay? And it's upright, and it's virtual. The reason why we say it's virtual, because there is no image that develops on the other side. If I take a film, for example, and expose it from the other side, I would not get any movie coming out of it. I wouldn't get a picture out of it, okay? So there is nothing on the other side. So this is called the virtual image. It's not real image. A real image, if you take a film, for example, and put it there, it's going to develop. And it's upright. Upright. Okay? And the magnification is equal to 1, actually, in this case, because it's the same size. This is this kind of mirror. Now you have other kinds of mirrors that you can encounter. First, let's talk about the concave mirror. For the concave mirror, basically, it has a focal point, meaning that rays that come from infinity, they will always pass through the focal point. So anything that comes very far away is going to pass by the focal point. So if you have an object in here that is sitting in here, for example, okay, then you can form the image following the same thing. The angle of incidence is actually this angle. Here is the normal to it. And the image will form somewhere in here, okay? If you follow this construction, the tail will go here, and you need another beam, actually. There is another beam in here that goes in here, and that will meet with this one in here, and this is where the image will form. The image in this situation depends on where the object is. So this is called the object. And this is called the image. If the object is on the other side of the focal point, like my drawing in here, the image is actually upside down. So it's not upright, it's inverted. It is real because if I put a film in here, I'm going to find something that develops off of it. So this is a real image. And the magnification usually is less. M is less than 1. The image is smaller, okay? If the object is sitting less than the focal point, the image actually is going to form on the other side. It's going to be a virtual image because there are no beams on the other side. And it's going to be upright. And the magnification is going to be usually more than 1. Okay, I'm taking the magnification in absolute value, okay? Because the magnification in here is going to be positive, and in here is going to be a negative magnification because it's inverted, actually. Okay, so this is basically in a nutshell. If the object sits right on the focal point, there is no image. Or the image is at infinity, very far away, cannot reach it. It's on the other side of the universe. So this is for a concave mirror. Concave mirror. Now for a convex mirror, convex mirrors, I know some of you are doing the lab for physics 11. This is how it looks like. It's shaded this way. Okay. The object is always in front of the mirror. So the object is in here. Well, the image will always be virtual. The image will always form in here. Okay, depending on how far this object is, it's going to be always has less than a 1 magnification, okay? But the image is always going to be virtual. So this is a concave, convex mirror, okay? And it's going to be upright. And the magnification is going to be less than 1 in this case, okay? Absolute value or not absolute, it's going to be always positive. The, excuse me, the other object that we're going to talk about are the lenses, okay? The lenses, they focus on both sides. So if the object is on one side here, the image will form on the other side. Now, usually, this is a focusing lens. This is actually convex lens. Okay. So if the object is outside of the focal point, you're going to have the image that forms on the other side is going to be inverted. It is going to be real. So the image is inverted and is real. And in this situation, the magnification in absolute value is less than 1. Okay. If the object sits below the focal point, the image will be virtual because it's going to be on the other side, and it's going to be upright, and it's going to be the magnification is going to be more than 1. When the object sits right on the focal point, there is no image again. It's going to be out of the focus area. The last object I'm going to consider is this diverging lens or concave lens. Again, the object sits in here. The image that forms is going to be on this side. Okay, appears to be from the other side. Depending again, so it's going to be an upright image. It's going to be virtual. Okay, and the magnification is more than 1, depending again on where this object is sitting. I'm going to ask you to do the following. Every person of us, every one of us has a near point. Okay. So you're going. If you're wearing glasses, you need to remove the glasses. If you're wearing those, that's the third task of the day. If you're wearing the lenses that you put on your eye, you need to remove them. You're going to take an object, okay, extend it as far as you can, and like this panel you have in here, okay, and bring it closer to your eye. Try to close one of the eyes just to see, and do it with the other eye. And you're going to bring it closer and closer until you lose focus, okay? So mine, I lost focus already, way back, okay? So I think I'm in here, okay? I lost focus, okay? You need to find where you lose focus. You will see this, first of all, depends on your age. If you're a young man, or if you're for babies, the near point is very close, okay? Where they start to lose focus, okay? When they get older, when a person is of an average age, basically around 20, 25 years old, most of you probably are at that age now, your focal point, your near point should be about 25 centimeters, okay? And I don't want you to report the data, okay? Because I don't want you to reveal something about yourself that you don't want to. So do not say, this is my near point, okay? I can report it, but you don't have to. You should not, really, okay? Now, as you get older and older, the near point moves further and further, and that's why you will be finding yourself basically putting glasses so that you can read the screen, because the screen is actually, you need to bring it closer so that you can see it, okay? So anyway, so you want to find the near point for yourself, okay? And do the task, basically, that this is what I did, and what I want you to do, actually do both eyes, and tell me if you're finding the same result. For me, it's a different. I have better focusing eye with the right eye than with the left eye, okay? So that is what I want you to do. Yes? If you go to an optometrist, this is some of the tests that they do for you, is to find your near point, because you would want the object to come to around 25 centimeters. The thing with it is, objects at infinity, like the tree, for example, I'm looking at it outside of the mirror, looks perfect to me, looks sharp, okay? But if I get closer and closer to, for example, one of the objects to it, it starts to become fuzzy and fuzzy. As a matter of fact, it becomes completely fuzzy. So when I'm too close from it, so that is basically what the near point is. How close can you get to an object and it stays sharp? I want you to measure it for yourself, okay? Find something about yourself. Are you more than the average? In other words, is your near point less than 25 centimeters? That is what more is. Better than the average person? Or are you average? Okay? Or are you less than the average person? Okay? And I want you to report whether both of your eyes are reporting the same data or not. Do you guys understand the task? I don't want you even to say that you're better than the average or worse than the average. I want you to just report on the two eyes in here. Got it? Because you have a lens in here, and that lens is supposed to bring the image right on the retina. Sometimes it doesn't put it on the retina. It puts before the retina or outside of the retina. And but for far away objects, they should really focus for you. Got it? Everybody? Yes, for both eyes, Jeffrey. And you tell me if both eyes are measuring the same or one of them is better than the other. That is not intrusive at all. It should not really reveal anything. Very good. So we talked a lot about this image formations and how the law of reflection works, and it's the basis for a lot of the images. Actually, I talked more also onto the lenses, and the lenses, they use the refraction. They don't use the reflection. Some people, they already put comments. No, that's from chapter 15. Again, the angle of incidence, maybe the incoming angle of the perpendicular. So again, with respect to the perpendicular, this is the incoming angle, okay? I made big fuss over this one in physics 11, and actually with you guys too, okay? The normal is the perpendicular. So again, this is the angle of incidence, this is the angle of reflection. Both of them are identical in the case of reflective materials, okay? When you have reflection. And this is the image formation I was talking about earlier, how images form on a flat mirror. Okay, again, we talked about concave mirror and we talked about convex mirror, okay? So for the convex mirror, the object is, the image is on the other side. No, yeah. And for concave mirror, it's also the other side, okay? For this situation, depending on how far you are from the focal point. Diffusion happens because of the fact that you have the beams are hitting when you have grooves in here. So the angle of incidence, the angle of reflection starts to deviate, and because it's actually the reflection is right in the edge in there. So now the beams are going in all over the directions. So this is an undesirable effect. You need to have the surface as smooth as possible in order to eliminate this effect. The refraction, I mentioned it, the fact that you have an angle of incidence in here and the angle of refraction, and they're related with that sine wave sine function, okay? The sine of the angle of incidence times the index of refraction, namely how fast light is moving in one medium versus how fast light is moving in the second medium. That is the index of refraction, I'm sorry, and times the sine of this angle are equal. So the mathematical formula, I don't know if it's given in here or not, is, let me stop quickly in here and show you the mathematical formula, because at least for those sitting in physics 11, they needed that. And they actually were able to find the speed of light in the second medium, the lucite. So what we have in this case is, again, we have now the medium that separates them. This is the normal. This is the angle of incidence. I have an N1 for the index of refraction, namely light in here travels with C over N1. So it's less than C because N1 is more than 1. So when you divide by a number more than 1, you're going to have, at best, it's equal to 1 for the error vacuum. Okay? For any material other than this 2, other than vacuum, actually, it's more than 1. So this is the angle of incidence. So what this law says is the index of refraction, namely the ratio of the speed of light over the speed in that medium. And the speed of light is fixed number. Okay, it's like 300 million meters per second, doesn't change. So it's mainly this how fast the light is moving in that medium, times the sine of the angle of incidence. I know some of you did not take trig, but the law has to do with the sine. And I mentioned the fact that Mr. Feynman was basically documenting that this is the only thing that the Greeks have documented. You think that the light is going straight out, but it's actually refracted. It's broken, if you wish, okay? So this is the angle of refraction. Again, the index of refraction in the second medium is N2. So this would be N2 times sine theta R. So if you don't know what the sine is, just you have a calculator, pick it up and put a number in there and hit the button. You're going to get a number out of it, okay? It's the ratio of the opposite over the hypotenuse from right angle triangle. But that's the law, okay? If you don't know the math for it and you don't use it, you don't care for it, all you need to remember is if you're fishing and you see a fish in the pond, do not reach out and grab it because it's in the wrong direction. It's actually slightly below, okay, at a refracted angle. For some reason, birds, they know this, okay? They come from very high in the sky and they go straight down to the fish and they grab the fish right in there. I think the bird, while it's coming down, it does a lot of calculations in there and uses the sine divided by the index of refraction of water, depending on the temperature of that day, and grabs the fish. Have you guys seen that on Nature Channel movies? And we struggle. I personally struggle with that, okay? You see a fish, you try to grab it, but it's not there because it's not there, actually. We had to learn that in school and how to do the math, but for some reason, yeah, actually, they somehow, I believe, Kyle, that these birds, when they're growing up, their parents teach them about these things. They have a calculator, they teach the math, and they do the sine, and they know the index of refraction for water, and they basically go and do it. That's what my feeling is. I'll have to really find where they learn that. We'll have to find the school where they go. Okay. I think they hide when they do that. But for some reason, they know it very well. Okay. Here's another fun experiment that you can do at home. Take a cup of water. Try not to get a glass, okay, that is transparent. For example, a mug, for example, of coffee. And put a penny in it, okay? Penny because you can see the color for it, okay? It's a different color. Or if you don't want that, you can put a quarter or a nickel, whatever you want to. And move back away slightly from it, okay? So if the cup is sitting in here, move back so that you don't see, don't put water yet, okay? Just put the cup with the penny. And you're looking and you see now the penny, move back slightly until the penny is completely disappears on you. You don't see it. Then have your friend or your brother or your sister or your mother or somebody pour water on in the cup, okay? And you will see, without moving, without anything moving, that again, as the water level starts to rise, now the penny or the quarter or whatever you put in that cup starts to appear to you. And that is because of the law of refraction. The refraction, I'm sorry. Because the light is refracted, and now the penny appears to you that it's coming from the other side. Now it looks like it's in here, but it's actually in here. So while you're standing in here, you see the beam, it's coming straight out, although it's broken, but it starts to look to you and you can see it and it appears to you. So that's, again, birds know that that's not correct. They know that the penny is on the other side. Okay. Does this sound fun? Can you guys try to do it at home? Again, take a cup that is not plastic, okay? Not plastic, I'm sorry, not, how should I say? Not glass, okay? Because you may be confused seeing it from there, so you say, okay, I see it through the glass. No, make anything like the mug, for example, that is deep enough, a little bit, not too deep, okay? Because if you get it too deep, then no matter how much angle you don't get to it, okay? Slightly deep, okay? Put penny or a quarter in it, it doesn't matter. And then move back slightly until it completely disappears on you. You don't see it anymore. Then start pouring water in it, and you will see it appearing. Don't come closer, stay where you are. You should be able to find it again. Okay. Again, I talk about the index of refraction being the ratio of the speed of light over the speed in the medium. Because light, when it goes through a medium, like water, for example, it's absorbed by the water molecules and then released back. So while it's moving between the different molecules in this case, or the different atoms in this case, it's actually traveling with the speed of light. But in between them, it's being absorbed. So slow down. So that's what that index of refraction really reflects. Or when it goes through the glass, the same thing. So this is what I was talking about in terms of the fish. So when I see it, I think the fish is in here, so I try to grab it, but of course the fish is on the other side, so it's going to move away. Nose. The law of refraction in this case gives you that illusion too of the trees being reflected and the as if you have water in here actually. Then we'll talk about the dispersion. How far are we? We'll still have quite a few slides to go through. Again, I mentioned that the light is actually broken down in here and disperses. And based on the dispersion, it's going to be separated to different frequencies. Okay. So in here, first of all, it's refracted once. So the white light comes in, refracted once, reflected again. The reflected lights, they come exactly how they leave. But then when it's refracted one more time, it's going to give me that. So there is a 42 angle degree for red and a 40 degree angle for violet. And this is just for violet, for the blue and violet, of course. And this is just enough to give me that effect that I was talking about. The separation between the colors, okay? And that is how basically because you're sitting in here, you first of all will be hit by the blue and the red, and that is how the light will appear to you that it's different. So this is where your eye is. From this droplet, you will have the red. From the other droplet, you will have the blue. And you look at them and they're clearly separated in the sky, okay? And that is how the rainbows form. Okay, so this is how when rain is coming and the light is hitting them, so that's what you see. That is basically the rainbow forms. Actually, sometimes you'll be lucky enough to get a double rainbow. And actually, over the weekend, I saw the double rainbows. Okay, I was driving from soccer and I saw them. Nobody came to soccer, only 3 people plus me, 4 people. Okay, so Again, the total reflection, I mentioned the fact that the light that comes from one source can be also opposite from the other side. And now you can have a total reflection when the light, first of all, this is the maximum angle for which the minimum angle, if you're coming from this side, with which you still have a little bit of reflection. And then after that, it's going to reverse course. This has tremendous applications in something called the fiber optics, for example. Because you can use tubes and then send a light, and that light will travel from one to the other side. So this is what new technology for the internet is using, actually. So it brings me to a point. The fish can move just enough so that it's not being picked up by the fisherman, doesn't even see it. Again, the law of reflection and refraction in this case is used extensively for the case, for example, of lenses, where you can produce parallel beams to the base. And these beams, as they come parallel, they go from the other side and they reflect so that you can see objects. This is used, for example, in binoculars. It's used also in microscopes. It's actually used also in telescopes to some extent, okay? All of the optical devices in here. And this is the fiber optics I was talking about in terms of the internal reflections being total. Lenses, there are two main types. Again, they are diverging and converging lenses. The converging lenses are the convex lenses, and the diverging lenses are the concave lenses, okay? And again, we'll talk about the focal length. The focal length, this is a characteristic of every length, and also for the mirrors, the non-flat mirrors. Actually, the flat mirror has also a focal point, which is infinity. It focuses on beams at infinity, okay? Because if you send a beam from infinity, it's going to go to infinity from the other side, or appears to be coming from infinity. Okay, image. Again, we talked about the fact that it's it can be inverted in this case, okay? And this is what I was talking about. This is the flower. When you use, for example, a magnifying glass in this case, or a magnifying lens in this case, it appears to you that it's coming from the other side, this big. So it amplifies it, magnifies it. So what you're looking at, when you take your magnifying glass and you look at the object in there, it's the same object that was sitting in here. It's moved further down so that you can, it looks like it's very far away and it's bigger, okay, it's magnified. Because if we didn't really have that near point that I was talking about, if we really didn't have that effect, then there is nothing wrong with bringing anything up close to your eye and you can see you can see it as big as possible. So if technically you can look at a virus. You can take that, what is it, coronavirus, and get it very, very close to your eye and you see it big and amplified, okay? Do not do that at home. Even with magnifying glasses, you have to really be super, super cautious with that thing. But the point being in here is you needed this lenses because we have that near point that I was talking about earlier. Otherwise, if that near point did not exist, we can take any object and put it very close from our eyes and we should be able to see it. So that is what I was talking about earlier about the near point. So again, if you have an object that is too small for you, even if you bring it to the near point or past the near point, you still cannot see it. So you use a magnifying glass to move the image at least to your near point or further. And then the object will appear, first of all, magnified, and then appears clear to you. Again, this is the object is inverted in here in this case. I talked about the aberrations, and the aberration has to do with the fact that the light, the white light, as it goes through a medium, it's going to be refracted with different frequencies. And again, the different frequencies would fall at different points. So now you lost your focalization and you have a problem, okay? You have this problem and you really need to use a different lens of a different shape, actually, diverging lens to bring them back closer in here to correct that. Okay, this is in a nutshell your chapters, okay? I'm going to put assignments for you, and I will see some of you tonight at 6 p.m., okay? I must warn you that the lab is not complete. I already posted the assignments for that lab for Physics 11, and I'm still working on some of the details for that lab in terms of the instructions. So, I'm going to stop the recording first.